Good afternoon. I'd like to welcome you all to the Cactus Semiconductor educational session entitled ASICs. And what we're going to talk about today is what is an ASIC. My name is James McDonald. I am the Business Development Manager. I'm also co-founder of Cactus Semiconductor. We've been in business since 2002. My background, I've spent most of my career as an analog and mixed signal IC designer, and so I have approximately 25 years of experience in that area. And today I'd like to talk to you a little bit about what is an ASIC and why would you as a system developer potentially use an ASIC. We'll go over some of the development and guidelines, and then just real briefly just touch on a little bit more about Cactus Semiconductor. Again, this is an interactive meeting, so feel free to ask questions. So let's get right to the heart of the matter. What is an ASIC? Well, an ASIC stands for Application-Specific Integrated Circuit. There are really three types of ASICs. There are digital ASICs, analog ASICs, and mixed signal ASICs. So what does an application-specific integrated circuit mean? Well, it means that it is customized, so application-specific, so it's customized for a specific use. There are a lot of advantages to that. As far as what these categories of ASICs are, well, a digital ASIC primarily consists of logic gates, memory, microprocessors, microcontrollers, etc. Purely digital in nature. An analog ASIC consists of such circuits as amplifiers, voltage regulators, current regulators, op-amps, data converters such as analog to digital converters or digital analog converters, etc. And then finally the last category of ASICs are mixed signal ASICs, which is what most of the ASICs are today. And this is really a combination of two above. They're a combination of the digital and the analog. So once you develop your ASIC, it's usually put in a package so that you can assemble it onto a printed circuit board or a hybrid. And ASICs come in a lot of different packages. So let's talk briefly about what those packages are. So a package part typically can come in something called a QFN or BGA. Quad flat no lead is QFN, or a ball grid array. And these are fairly standard and they're low cost. The ball grid array in particular offers significant number of pins, higher pin density or interconnect to your printed circuit board. You can also take delivery of an ASIC as a bare die. And in this particular case, you take the die and you mount it, and then you bond down from the bond pads to your printed circuit board or your flex circuit. And this is called chip on board because you're literally putting that bare die onto the printed circuit board. And then of course you have to protect it in some way so that it doesn't get damaged, and so it's encapsulated with some kind of protective shell. Another option is something called bump die. And this is where you put bumps, or little balls if you will, directly onto the bond pads along the periphery, and then you flip it over and those bumps make contact to the printed circuit board. And unlike the bare die, this eliminates those bond wires of the chip on board. Slightly more advanced is something called wafer level chip scale packaging, or WLCSP. This requires a distribution layer, and basically what it does is it takes the pads or the bonds around the peripheral and it lays it out in a grid fashion, much like a BGA. You can kind of see this picture here where there's an X and Y grid of little balls or bumps. And then again, you can kind of flip that and bond that right to the printed circuit board. And the big advantage there is that the final footprint is the same as the die footprint. There's no overhead really in terms of X and Y dimensions associated with wafer level chip scale packaging. And then finally, we have stacked die. And this is more advanced packaging, where you're basically taking a number of die, so not just one die or one ASIC, if you will, but a number of die, and putting them into a single package. So externally it looks like one package, but you might have 2 or 3 die stacked on top of each other, and they can be connected between die to die, or from die to the package to the printed circuit board. You could imagine something like a wedding cake where each die gets a little smaller as you move up, and you bond from one die down to the next die down to the base layer. You could also have these die placed next to each other in a horizontal fashion as well. And basically you can create a system on a chip. You can imagine, say, a custom ASIC, and then maybe a microprocessor chip, and then maybe a small RF chip on the top. Something like that might be a multi-stacked die package. So why would you use an ASIC? Invention. Basically, there's nothing off the shelf that works or works very efficiently. So that's certainly a reason why you would consider an application-specific ASIC, because you can basically order exactly what you want. Bill of materials reduction, that's another reason for an ASIC. You have a whole number of independent off-the-shelf components, and you know that you can integrate those and put them into a single ASIC and reduce the bill of materials, and with that hopefully the bill of materials cost and that the development cost associated with an ASIC can be gained by reducing that bill of materials and the assembly cost, since you're only basically using 1 or 2 components now rather than, say, having 10 or 12 components to assemble. Your assembly cost should go down as well. System power reduction. So off-the-shelf products are general purpose. Because of that, they tend to try to make the device broad use, broad applications, and often that's the case. They're burning more power and trying to maximize performance that you may not need, and power that's just going to be wasted for you. System size reduction, again, if you can integrate number of components into a single ASIC, you're going to reduce the size. Also, off-the-shelf components may just have unwanted features that you don't need. If you can eliminate those, again, you can reduce the footprint. Also, by reducing the power, which we just talked about, if you reduce the power, you have an option to reduce the battery size, because basically the power often drives the size of the battery or the battery capacity. So if you can reduce the power, you can reduce the battery, you can reduce the size again. So those are very synergistic. Now, there are some challenges associated with the ASIC, along with some benefits. So let's just talk briefly about those. As far as the challenges, development costs. We can talk a little bit more about development costs, but there is a non-recurring engineering cost to develop a custom ASIC. Obviously, the schedule is also another challenge, and we'll talk in detail about that. Off-the-shelf components, you can buy them right now. Development risk, that's another challenge. Off-the-shelf components exist today. You know exactly how they work, whereas with an ASIC, you're developing it for the first time. Your first silicon, there's always a chance that there's going to be a need for a second revision. And then the sole source aspect of it. Many off-the-shelf components have multiple sources. Typically for an ASIC, you're going to be engaging with one company to develop that ASIC for you. So what are the benefits? Well, intellectual property protection. If you have a board that consists of off-the-shelf components, it's going to be much, much easier to reverse engineer that board and figure out what exactly your design is doing. If you have a custom ASIC, it's significantly harder to determine and to reverse engineer that ASIC and determine what you're actually doing there. You optimize the feature set. In other words, you get exactly what you want, and those features that are important to you, that are critical in performance, you optimize for, and those that are not, you can take advantage of, as we talked about, by getting rid of them or reducing the power requirements. So we optimize performance, we optimize feature. We talked about the size reduction that you can gain, the power reduction as well. Improve reliability. I hinted at that a little bit ago, where if you only have one or two chips that you're assembling, you're going to have a lot more reliable hybrid or printed circuit board than if you have 12 components and a lot more interconnect, a lot more solder joints, et cetera, et cetera. You minimize your supply chain rather than buying, say, 12 components from 5 different semiconductor companies. Maybe you're just buying them from a couple companies, so you really reduce the number of supply chain partners that you have to manage. Obsolescence protection. You're engaging directly with a company to design your ASIC. They have a vested interest, and you're going to be able to work with them directly in terms of any type of supply concerns. Whereas if you're buying a standard product, you might get a notice that just says, hey, we're obsoleting this part in a few months, you're done. And of course, we already talked about cost reduction. So you have to trade off that cost reduction of the ASIC versus all those discretes and the assembly from the development costs. And when will you get a return on investment? So let's talk a little bit about some of the misconceptions. And these misconceptions probably 20 years ago, 25 years ago, probably were true in many cases. But as we advance in technologies and capabilities, we believe these are clearly misconceptions in today's world of ASIC development. So one of them is an ASIC will take $2 million, 2 years, and it won't work. Well, there's been dramatic improvements in the fab processes, so the silicon processes, the modeling of those processes so that you can simulate and know exactly what you're going to get before silicon even comes out. And then, of course, the simulation tools themselves have improved. There are many more simulation tools to model different artifacts that weren't able to be modeled in the past, and the tools themselves are simply better. Cost, schedule, and risk have improved in recent years. We are very, very good here at Cactus at getting first pass fully functional silicon. And perhaps you might need a little tweak or something, but you're not going to go through these numerous revisions and end up at the end still not having a device that works. Successful ASIC teams are going to use approaches that mitigate risk, and we do that in many ways by staging silicon halfway through the process. So if we do need to make a tweak, maybe we can use those wafers that are staged and we can do it much quicker. We build in extra devices, extra circuits, so that we can make those changes in metal up rather than starting over at the very beginning of the process. So risk mitigation plays an important role. And as I already mentioned, most Cactus ASICs are fully functional on the first revision. Another misconception is ASICs cannot possibly reduce the cost. So you need to look at the return on investment. It may take several years to get that return. You really have to look at your volume. You have to look at your cost of your current bill of materials, and then you have to compare it to the cost of the ASIC and the reduced bill of materials and the lower cost assembly. And if you have some good volume, and then you can get that return fairly quickly, maybe in a matter of 6 months or less. With guaranteed volume as well, it's possible that you can amortize some of that NRE, that non-recurring engineering cost or development cost, in the average selling price. So maybe the first year the price is a little bit more, and then we reduce it over time as we get that return on investment. Okay, let's talk a little bit about ASIC development and some of the best practices here. So we look at development in 4 phases, starting with phase 0, which is a feasibility, definition, ASIC specification phase. And this we really see as the foundation. Think of it as the foundation of your house. It needs to be solid. You need to know what the issues are, what the risks are, and you need to have a well-defined ASIC development spec before entering phase 1. And if you do that, everything is going to go a lot faster and a lot smoother and have a much higher probability of success. So once you have that ASIC design to spec, that is what's used in phase 1, where we're doing the design, the simulation or verification, the physical layout, and the physical verification. And in that phase, we do frequent design reviews, a minimum of a couple, but usually more. We have a preliminary design review before we start layout, and then we have a critical design review at the end. And customers are invited to participate in those reviews. Once we agree we're ready to go and we have a good design, then we move that into phase 2, which is where we're going to start fabricating silicon prototypes. We're going to get them assembled, and we're going to evaluate those prototypes. And once we do a screening and evaluate those prototypes, we provide the customer with prototypes so that they can look at them at a system level, because we're much more focused on the ASIC specification and meeting those requirements. But in many cases, you can meet the ASIC specification requirement, but then not meet the system level requirements. So we want the customer to be engaged in evaluating those prototypes at a system level. And finally, phase 3 is where we start talking about production. That's where we're going to do production test development. That includes software and hardware, as well as qualification, developing the hardware for qualification and running qualification, such as hot temperature op life, ESD, latch up, temp cycling, etc. So those are the 4 phases, and throughout those phases, we're going to do project management throughout all of those, and that includes weekly reports and weekly conference calls. The key here in the development is you want no surprises, and you certainly don't want your customer surprised. Now, does that mean every ASIC comes out perfect the first time? No, it doesn't. So, we can predict the likelihood of a first pass success based on our experience. As I said, most of the ASICs, if not all of them, come out functionally first pass, but still there may be some parameters that we need to tweak in. So we talked a little bit about risk mitigation. Some additional things we can do is we can do test chips on some of the embedded circuits or high performance circuits. We design in contingencies, and I talked about that. Extra devices. You can rework the silicon itself and cut metal traces and kind of create metal connections on the silicon. And you can do that to develop a couple working prototypes. And then you can go back in the fab and make those changes permanently. And I already talked about holding wafers midway through the process so that you could use those wafers and maybe make poly up or metal up changes. Bottom line is you should budget for it, both in terms of schedule and cost, for a second revision. So let's talk about the scope of ASICs. We'd like to categorize ASICs in 3 scopes or 3 bins: small, typical, and large. So how do we define that? Well, small scope, minimum invention, maximum reuse, moderate performance and complexity. A typical scope, well, we're going to have some invention, maybe let's say 20%, some reuse, moderate to high performance and complexity. And in a large scope, a majority of the ASIC is invention, new, something that hasn't been done. Likely hasn't been done before, or maybe it just hasn't been done by Cactus or your vendor. Minimum reuse and high performance and complexity. So what do these scopes mean in terms of the project itself? Well, we have this little graph here, and on the y-axis you see weeks of development time, and on the x-axis you see the 3 bins we talked about in terms of scope: small, typical, and large. And you can see, just to kind of summarize it, the development time of a small, typical, and large ASICs in weeks. And you can look at the small scope, and it's 47 weeks, so less than a year. Typical is somewhere around a year and a quarter, let's say. And a large ASIC is roughly a little over 2 years, actually. And one of the things to note, on the right side, you can see that we have little the 4 phases, and we've also included a Rev B. So all of these include a Rev B. So you can see that this is very reasonable and somewhat conservative in that it does include a Rev B. The other aspect is that you can reduce the schedule by assuming that phase 3 overlaps the phase 2. So when we're developing that hardware and software for production test, we can do that while the wafers are running in fab, and that helps save some time as well. So again, continuing with some of the guidelines, let's looking at your vendor and supply chain. An ASIC vendor's supply chain should offer a wide range of capabilities. So in other words, you want your ASIC vendor to pick the best process, the best technology for your device. You don't want them to be necessarily locked into saying, we're only going to use this process, or we're only going to use this vendor, because then they're often making trade-offs. Similarly, with packaging and test, you want the ASIC vendors to be able to deliver a wide variety of packages so that you can have the package that best suits your needs. ASIC vendors and suppliers should have ISO certification, quality counts. Again, we do a lot of work, particularly in the medical. We have a quality management system. We are ISO 9001, 2008 certified, and so are our vendors. ASIC vendors should use state-of-the-art design tools. We primarily use tools such as Cadence, Mentor. These are state-of-the-art. They are the leaders in their industries. And yes, they are not inexpensive. They are expensive. But if you skimp now, well, you're likely going to pay later in terms of additional revisions. And an ASIC development, at least in our minds, should have a high level of customer involvement. We have something called Customer First Rules, CFR, which also stands for collaborative, flexible, and responsive. And we want the engagement with our customer to be very collaborative. So Cactus Semiconductor is a turnkey ASIC provider. We do turnkey ASIC development and design services. We have a highly skilled engineering development team, mostly analog and mixed signal. We focus a lot in medical, low power, and portable devices and applications. Many of our employees have over 25 years of industry experience, and with our medical pedigree, that really comes out of the fact that several of us came from Medtronic. We work with a group of high-end suppliers. We talked about that just on the previous slide, for fabrication, production assembly, and production test. And as far as quality, again, quality counts, we are ISO 9001, 2008 certified. So that's it on what is an ASIC and a little bit about Cactus. Do you have any questions? You can send those in and we can answer them. We do have one question here about how do you pick the technology that you're going to use for wafer fabrication. So I talked a little bit about phase 0. That is where we make that selection. And basically, we get a spreadsheet together, if you will, and on one axis we list all the features of the device, your requirements, such things as do you have multiple voltage supplies? Do you have a high voltage? Do you have low voltage? Do you need memory? How much digital is on your ASIC? Is it a lot of digital, or are there hardly any digital at all? And all that is going to influence the process geometry that we select. So is it 180 nanometer, 90 nanometer, 350 nanometer, as well as what fab are we going to use? And some of that also could be dictated by volume. Do you have large volume or lower volume? And so out of phase 0, we will have a recommendation of what we want to do in terms of the vendor and the specific process node and options on that particular technology node. And all that comes out of phase 0. We have another question. How do you determine what to integrate and what not to integrate? That's an excellent question. So, it's kind of system on a chip versus, multiple ICs. We at Cactus talk about, and I believe we've published some papers on this, we talk about smart integration, not maximum integration. And by smart integration, what we're trying to do is we're looking at, is there already components out there, a component out there that exists, and is there a reason to integrate that if it already exists? So you could imagine we look at typical integration, and typically a system has a microprocessor, maybe some kind of RF communications, and an ASIC. And that's what most of our systems look like. And you say, well, why not integrate the RF or the microprocessor? Well, in many cases, the technology that we're doing the ASIC on doesn't lend itself to the high digital content of a microprocessor, or perhaps the RF performance of an RF IC. So does it really make sense to make those compromises and try to find a process that can do all three, but not really do any of them well? Also, you're going to add risk and development time if you're integrating that microprocessor or RF that already exists today. And if you do integrate it, then you're locked in. So if we integrate that microprocessor and you want to change that microprocessor, we've got to change the ASIC. Whereas if you don't integrate it, you can kind of follow the technology evolution in time as that microprocessor gets upgraded, or you want to add more memory, you can select a different microprocessor, and you don't have to change the ASIC. So we're very much an advocate of looking at smart integration and not necessarily maximum integration. And the other option, when we talked about packaging, we talked about the multi-chip die stack. So rather than maybe integrating it on one monolithic piece of silicon, we could stack those die in a package. And then if we want to change out one of the microprocessor, for instance, we may be able to do that. Now, there are some risks, and it may not work depending on where the pads are and things like that. But that also offers an alternative to integrating it all on one monolithic piece of silicon. Both good questions. All right, so let's go ahead and wrap this up. I want to thank you all for your attendance. It's greatly appreciated. If you have further questions or would like to explore whether an ASIC is right for your system electronics, please feel free to contact me at james.mcdonald@cactussemi.com. You also have my phone number. In addition, Andy Kelly, he is our system and IC architect. He has over 25 years of experience. He is a wealth of knowledge, and you can contact him as well at andy.kelly@cactussemi.com. And again, thank you very much for your attendance.